We'll have to be a tiny bit more careful to get the equation of motion for a system with Coulomb friction, and that's because Coulomb friction is nonlinear. So to make sure we get this right, let's draw the free body diagram. So we have a mass, and we'll assume there's gravity holding the mass to the surface, so there will be a gravity force acting on this mass of mg. Now there has to be some counteracting force, or this would just fall. So the table has to exert a counteracting force N, and since there's no acceleration, we're assuming no motion in the vertical direction, N ends up being equal to mg. We could have got that from the sum of the forces in the y direction. Okay, and what about friction? Well, the tricky thing about friction is we can't say which direction the force is until we know which way the mass is going. So, for example, if we had x dot greater than 0, we know the friction will want to slow the mass down, so we'd have a friction force here, F equals mu n. But what happens if the velocity was the other way? If the mass was actually moving in the opposite direction, then the friction force would act the other direction. We'd have, again, F equals mu n. So, what we can do to deal with this is to use the Signum function, which is Sign of a number, x, is equal just to +1 or -1, depending on whether the number is positive or negative. So what we end up with is if we set the sum of the forces in the x direction here equal to mass times acceleration, for the force we have negative mu n, and that will be equal, that's the only force we have applied, that will be equal to the mass of the block times its acceleration, x double dot. And now we'll add in the Signum function. So if the velocity is positive, then we'll want that force in the negative direction as we've done here. So we'll just add in here Sign of x dot. And what this will do is if x dot is positive, this will be a force in the negative direction, and if x dot is negative, this will become -1, and we'll change the sign of the force.